Okay. We live? All right, let's get started, folks. Last few folks trickling in. All right, welcome to my session on AWS Encryption Services. My name is Ken Beer, General Manager of the AWS Key Management Service. Just as a show of hands, how many people out in the audience are using some type of encryption service from AWS? Excellent. Love to see it. All righty. So what we're going to talk about today is a little bit of a theoretical discussion about how we think about encryption in AWS. Understand all of the various encryption and key management services that we offer to try and make it easier for you to secure your data. And ultimately, what I'd like you to leave this session with, if you don't already believe this, is that it is in fact safe to trust AWS with your keys. So, why do we encrypt in the cloud? For the past, 10 years, since people have been putting information up in IaaS providers like AWS, you do it because you're told to, for compliance. You do it because you think it's the best way to protect the security of your data, given that you no longer control the data center or the physical hosts that are storing your data. You do it because you know that there's shared infrastructure in the cloud, and you want to protect yourself from all the other customers that are also using that cloud provider. Or you're doing it because you're trying to protect yourself from your cloud provider. We try to distill all of these kind of external reasons for encrypting into two primary ones, which is minimizing unauthorized access, both at a physical and a logical dimension. Now, I've put in the standard CIA of confidentiality, integrity, and availability, just as a reminder, because I think that's a good linchpin to think about when you're looking at security. It's very easy to over-index on confidentiality or integrity. But availability starts to become very important as you're adding encryption, because you're creating more complexity in your data and how you access data, and you want to make sure you're not giving up on availability and performance. So let's drill down a little bit on minimizing unauthorized physical access to data in the cloud. Now, I'm going to break down the classic locations of data into data in transport, at rest. I'll talk a little bit about data in use. So in transport, you're primarily concerned about data on the wire from one physical host to another physical host. Since we introduced the Snowball and Snowmobile services, I'm going to assert that data in transit also includes stuff moving in a truck from your data center to our data center. Certainly data at rest, you are going to have to rely on the physical security parameters that are enforced by your data center provider. But you can also rely on various encryption modes. So if you start at perhaps the smallest unit, the block of data, move up to the file, the directory, the file system, even full disk encryption, right? Lots of third-party tools, lots of open source tools that allow you to protect data at rest. When it comes to protecting data in use, again, the physical host is inside our data center, so you have to rely on the physical security properties of the data center operator to ensure that unauthorized individuals don't get access to touch the host, to plug in to the console network, to insert a USB drive where they shouldn't, right? So what about logical access? So you're kind of giving up a lot of the physical security to the data center provider, but from a logical access standpoint, you do have more control. Certainly defining network routes. So how can data move from point A to point B? Can you put encryption on the wire using technologies like TLS, IPsec, or MACsec, and these layer 3, layer 4 technologies? Trying to secure data at rest, fundamentally you need to reason about access controls on the data. You need to try and move your mental model from providing a very robust perimeter of access control and security around an unknown number of hosts and resources, and zero in on the actual resource. And given that AWS is, at its core, a collection of a few thousand APIs and maybe a few hundred resource types, you can use the reporting tools inside AWS, and for that matter, any cloud provider, to reason about access controls on an individual resource. So what about data in use? What are the logical access controls that you would want to be concerned with? Certainly, as we talked about before, you want to ensure that unauthorized individuals can't do memory dumps, can't somehow get access through the hypervisor or up through the underlying operating system or the hardware itself. What can you do as the owner of the data? So there's been a lot of discussion about encrypt in memory. And I'm somewhat ambivalent about this as a security control. I understand that you want to make sure that your memory space is secured and other processes owned by unauthorized individuals cannot run inside your reserved memory space. But having your data reside encrypted in memory may or may not be the right choice. It really depends on how you want to use your data, right? If it's okay that all your data is encrypted and you can do meaningful operations on your data encrypted in memory, okay. But I don't think it's a safe control to say my data will always be encrypted in memory. Because if you want to do some type of range search, you want to do some complex machine learning algorithm, you're going to have to expose plain text. And so we find most of our customers understand that plain text data is going to be in memory, and they want to be assured that that memory in fact belongs to them. Or if it doesn't belong to them because they are outsourcing the processing of their data to another service, they want to make sure that that memory is sufficiently protected. So, you'll notice in the previous two slides, I'm talking a lot about control. Control to policies for access, control of encryption keys as yet another access control mechanism. So, who inside your organization cares the most about control? Well, the developer that needs to use the keys, hopefully they have been trained on security best practices and they understand that they should be using keys in a proper way. But I would argue they fundamentally care the most about availability, right? Software developers get paid to ensure that applications work well and they accomplish the task. It's often the IT security team that is making decisions about how resources should be accessed, how they should be controlled, right? As you get to a large enough organization, your development organization has to follow rules that are set forth by IT security. And what we find is a lot of IT security teams will set up dedicated AWS accounts in which they have highly privileged administrators. They will create KMS customer master keys inside those accounts and then delegate their use out to other accounts in which developers can use to build applications. So if you have IT security that's setting the rules and the software developer that is then obligated to follow those rules, how do you as an organization ensure that those rules have been set up properly and are being followed in perpetuity? Well, that's the job of compliance. Right? So they want to do verification of how this is set up because they are the ones responsible for proving to themselves and external auditors and external customers that you are doing the right things to minimize unauthorized access to data. Does this mean you can make it perfect? No. Right? I use the term minimize on purpose. Because as you build much more complex rules and complex environments, there is, of course, the opportunity for you to misconfigure. But if you think about these three personae, or these use cases, as you're designing your security policies, you will lower the risk of misconfiguring and ensuring that only the right people have access to encrypt data and the right people have access to decrypt data. So let's drill down a little bit more on what control means. Because when I talk to customers on a weekly basis, one of the first requirements they come back with is, we want to put sensitive data in AWS, but we have to maintain control of the keys. So if you're talking about control of access to data in general, then there's an assumption, and I think this is a pretty fair assumption on both sides, that you as the owner of the data are going to own your identity. You have a way to prove your identity, whether it's a password you use to log into the console, multi-factor authentication device that augments that authentication, and more generally, API signing keys. So if you're programmatically using AWS, your signing keys are unique to you, and you are responsible for their physical and logical security, which is why we are constantly searching for strings that look a lot like AWS access keys out on GitHub and other public sites to remind people that they need to secure those. The other important aspect here is that you alone can modify any type of access policy. So the AWS Identity and Access Management Service allows you to do this. You can create certain resource-based policies within services like S3 or EC2. So now let's drill down on control over encryption keys. What does that mean? Well, certainly you need to make sure that keys are durable. Why? Well, unlike authentication keys, which can be rotated and deactivated and reactivated, if you lose them, as long as you don't have a rogue operator that gets a hold of them, you can always create new ones. But encryption keys must remain durable. You cannot lose an encryption key, else you lose access to the data. So you either have to trust your cloud provider to create and never lose keys, or you might have a model where you keep a master copy yourself, and you allow a cloud provider to use a key for a certain period of time. Keys are highly available. So this becomes one of the, call it conundrums for customers to consider, which is they believe that in order for keys to be secure, they must always possess them, store them. Keys are in my data center, right? If you want to use encryption keys, AWS service XYZ, you will come back to my data center over the public internet, over Direct Connect, however we can make it work. And I will argue that this is contradictory to your goal of having keys highly available, right? There is no AWS service that offers an API with any degree of SLA, whether it's public or private, that takes a dependency on your network, right? So this idea that you're going to ask, let's say, Amazon Redshift to take a encrypted snapshot of a cluster and spin it up for you, and the success of that cluster launch is dependent on Redshift being able to drill through your firewall and access a hardware security module in your network and decrypt a data key, right? That just doesn't work. It certainly can't work at scale. So the other important thing is that since we look at encryption as yet another form of access control with policies on who can use keys and under which conditions, you have to be the only person who can modify those policies. So just like general access control policies in IAM. The other important thing for the compliance person in your org to be happy is that you have to have a record of every time keys are used. Because the mental model here is that you can certainly say this particular piece of data was touched or downloaded from an AWS service, but it was encrypted. So the only way that you know that the plaintext data was accessed is if the encryption key was accessed. So having an authoritative record of all access to encryption keys helps the compliance team close the loop and say, yes, this access that happened at this date stamp was in fact expected. Or it wasn't. And therefore, I'm going to build something like a CloudWatch event for anomalous behavior. Okay? All right, so let's move into the two different categories of security. So I'll start with data in transport. So what does AWS offer today for data in transport? So if we start kind of from your EC2 instance and applications that are running inside your instance, Most people for the past few decades have understood the concept of virtual private networking. So we have 3 different options here, one of which is kind of a dedicated managed VPN option where we will connect to your VPC from a single remote network. So we have a virtual private gateway that manages this. You can aggregate this idea of virtual private gateway across multiple remote networks. We call that Cloud Hub. And of course, you can run your own VPN endpoint inside an EC2 instance and connect to it. So plenty of offerings in AWS Marketplace. You can certainly install your own solution. So this gives you your kind of layer 4 type security across the network. You can combine that with security groups, and together with VPC, you can encrypt, so you provide confidentiality and integrity for data going across the wire into your instance, into your custom application. So, bumping up a level for web-based APIs over HTTP, you can use TLS. So, how can you use TLS? Well, you can certainly install your own certificates running in your own web servers on EC2. Plenty of customers do this. You can actually import certificates into AWS and refer to them for use inside services like Elastic Load Balancing, CloudFront, and API Gateway. So this may reduce the time it takes for you to take a custom certificate that you got from some trusted certificate authority and apply them to the web front end or the TLS termination technology that you have running inside AWS infrastructure. So last year, in early last year, we introduced AWS Certificate Manager. And Certificate Manager is trying to solve a couple of problems. One of which is, how can we make it easy for you to get a public-facing, trusted certificate and do it without the time and the money that it costs to go through more classic providers. The second problem that ACM is trying to solve is, how can we ensure that that certificate and its private key is distributed securely down to the web server, the endpoint, the TLS termination site? The third problem that ACM tried to solve is, how do we make sure we can do rotation of these certs transparently? All right? So we say AWS handles the painful parts of PKI. Right? We will ensure the generation of sufficiently random RSA private key pairs and public private key pairs. Excuse me, while my presentation has a mind of its own. We will make sure that those private keys are only distributed down to ELB, CloudFront, or API Gateway endpoints when you ask them to be. And we will manage the automatic renewal and redeployment of these private keys. Just last week, we introduced domain name validation through DNS, in addition to email validation. And of course, the nice thing about this for ACM is that it's entirely free. So how many folks are using ACM today? Okay, good. All right, so the last option with TLS is, let's say you're building your own application, whether it's client-side, server-side, and you want to use TLS, but you are a little intimidated by using OpenSSL. I don't blame you. OpenSSL has become a bit of a beast over the past decade or so. And what we did with the S2N project, which stands for signal to noise, is we stripped out all of the extraneous code inside the TLS spec that comes bundled with OpenSSL and streamlined it so it runs faster. We ensure that it uses the most secure algorithms. It's all open source. We use it internally within AWS services, so S3 endpoints are using the S2N technology to try to improve performance and reduce latency. And if you want to take it and customize it to meet your needs, you're welcome to. Okay? All right, let me move on to data at rest security. So I've done this animation a few times over the years, so I'll go through it quickly for those of you who have seen it. But when you're trying to encrypt bulk data, symmetric encryption is really your only option. Asymmetric is useful for small amounts of data, but large multi-gigabyte files or streams of files, you really need symmetric data keys. When you take your plaintext data and a plaintext key and apply an algorithm like AES to it, you've got ciphertext, which you are assured by the proper implementation of the algorithm that the ciphertext is indistinguishable from random data. So now I will store that encrypted data somewhere, perhaps in an AWS service, perhaps you store it in another cloud provider, it doesn't much matter. But now I have a plaintext data key that has to be used to decrypt this data. So how do I make this available to people who are authorized to decrypt the data? I have to store this key. Remember I said durability of keys is paramount. I cannot store the plaintext key anywhere near the data. In fact, I cannot store the plaintext key anywhere that's discoverable. So best practice is to encrypt that plaintext key with yet another key. Now you've got an encrypted key and encrypted data, which you can store side by side. And you can marry the durability of the data and the encrypted data key together. So if you lose one, you're going to lose the other. Not that we want you to lose either, but at least you've got similar durability characteristics of each. Okay? But now you've got a plaintext key that you use to wrap the data key. What are you going to do with this? You can continue to encrypt and create what we call a key hierarchy. Right? At some point at the top of the hierarchy, you have to have a plaintext key available to be able to unwrap all the keys below it. That's where a key management system comes into play. Okay? So let me talk a little bit about the options for data at rest encryption today in AWS. And we split them into two categories. The first is client-side encryption. So client-side encryption is the idea that the point at which your data is, say, generated, made available inside the application, before you're transporting it somewhere, you want to encrypt it. Now, you need the encryption software to do this, and you also need keys. So what AWS does is that we give you some helper tools, if you would like to use them, to simplify the actual encryption of data. The AWS Encryption SDK is our most recent offering. There's 3 services that have dedicated clients that can facilitate the encryption of data, S3, EMR, and Dynamo. And you can use keys from anywhere. If you want to generate keys on your own desktop, you can do that. We wouldn't recommend that, but you can. You can also leverage keys from a service like KMS. Okay? The important distinction here is that you're responsible for the processing and the creation of ciphertext as well as their decryption. The other option is server-side encryption. So this says I'm going to rely on a protocol like TLS, or maybe it's IPsec, but typically it's TLS when you're talking about AWS services. And you're asking the service to encrypt on your behalf. So before S3 writes it to 3 independent storage locations, you want S3 to manage the encryption. So today there are 43 services in AWS that will support some type of server-side encryption. This list will continue to grow. In fact, by the end of the week, the list will be greater than 43. And by the end of next year, it will be much greater than 43. At some point, any AWS service that stores your data will offer server-side encryption. Now, all of the services, the way they implement encryption is that they integrate with the key management service. All right, so that's the only way that you can get a service to encrypt on your behalf, is that they will use keys that are generated by KMS. So let's dig a little bit deeper into the options for client-side encryption. So let's assume that you're starting with data somewhere outside of AWS. There's one model that says you encrypt using whatever client you want. You may use one of the helper clients that AWS offers. Remember, if you use something like the AWS Encryption SDK or the S3 client, AWS can't see your keys. right? It's just helper code running inside your Java, your .NET, whatever the platform might be. So you've now created ciphertext, and you can upload it into any service that accepts data. You can do the exact same thing from within an EC2 instance. So you can manage all of the encryption process and key management inside EC2. You can even call back into your key management system from AWS. So here's a model where, remember earlier I said an AWS service is not going to reach back into your network to access keys, but your applications running in EC2, you can do what you want. If you're willing to be responsible for the availability and the latency of calling back into your network, that's fine. You could optionally choose to have some type of key management infrastructure running in a different EC2 instance. Perhaps it's a managed service provider that offers a solution that runs inside AWS. You can also get your keys from AWS Encryption Services like KMS or Cloud HSM. I'll talk a little bit more about the differences between Cloud HSM and KMS. But the point here is there's lots of options. Since you are controlling the encryption code, if you want to use some of our SDKs, we are agnostic about where you get your keys. We do have an opinion about what we think is the easiest place to get your keys, but it may not be the right answer for you. The other interesting thing that you can do is that you can have keys kind of coming from your key management infrastructure and import them into KMS, and then use them from your own applications after the fact. Okay? So, drill down a little bit on the encryption SDK, because this has been a big area of investment for us this year. It will continue to grow over time. Why are we doing this? Because we think that with a service like KMS, we've provided a relatively useful set of server-based APIs for you to generate data keys to use inside your apps. Certainly the creation of master keys. They get stored inside the service and never leave. You can do rotation. You can use aliases to manage human readable names on keys. The service will continue to scale. We're in every commercial region in the world except China. And now the issue is that, well, if you're an application developer and you've gotten a 256-bit data key from KMS, now what do you do? Right? You're kind of on your own. And we are seeing more and more customers that say, I want to make sure that my developers have to make as few decisions as possible about cryptography when they're trying to encrypt data. So the requirements for developing the AWS Encryption SDK were, we want developers to understand two things. One, where is my data source? My message, my file, my stream. And they have to understand that anyway. And the second is a simple identifier that determines the provider of keys. Now, you could say, well, how is a developer going to know what the key provider is? Well, you as an IT security administrator, or those IT administrators in your company, can actually configure that up front and hand a package of the SDK, a custom build, to your developers, and just say, use this key provider. It may be, use this KMS key ID, right? You can hand them a custom version that only uses a particular KMS key ID. So now a developer knows, all right, all I have to do is pass my stream into the encrypt method, and out comes ciphertext. Your developers don't have to worry about bit length, mode of AES, IV needed for AES, data caching rules, and so on and so forth. Those levers and knobs are available for you to customize if you want, but only if you have the right people on staff who know what they're doing. So the defaults inside the encryption SDK are such that we make sure that you can encrypt practically an infinite number of streams under a KMS key ID, infinite number of files, objects, or streams. We just recently released this in CLI, which might be very interesting, especially as part of your dev test for folks to experiment with. So I recommend learning more about this, because this will be the future of how we are expecting customers to interface with KMS, and we think it vastly simplifies the experience of encrypting data. All right, so how does server-side encryption work? Well, server-side encryption uses this concept of envelope encryption, right? We can't, or we don't want to take your massive multi-gigabyte S3 upload and move it over to the KMS service to say, please encrypt. All that does is expose your plaintext S3 files to more hosts inside AWS. We want that to be encrypted directly at the web server when S3 accepts your put command. Okay? Same thing with EBS. You're creating an encrypted volume. We're not going to send your 8,000 provisioned IOPS going from your instance down to an EBS volume and somehow shunt that over to KMS to encrypt. Right? The laws of physics just won't allow that to happen. So instead, we're going to generate a unique data key inside KMS and deliver that down to the service to use on your behalf to encrypt the resource that you asked to be created. So the advantage of this is that we're just shuttling very small pieces of data back and forth between KMS and the service that you're using. You get a limited blast radius, so a unique data key per resource, whether that's per S3 object, which could be incredibly small number of bytes, or a multi-petabyte Redshift cluster. Right? That's the mental model to think about. Unique data key per resource. And with KMS, you only have to reason about the customer master key at the higher level. Right? You don't have to reason about billions of data keys. In fact, we don't even provide an interface for you to see what the identifier for the data key is. Because you know that that data key, after it gets used in memory, it will be encrypted under a master key and stored alongside your data. The only way for that data to be read is if that encrypted data key is passed back up to KMS. So all of the access controls are placed on the master key, what we call a customer master key or a CMK. Okay? The same model works with custom applications. In fact, the AWS Encryption SDK is using envelope encryption under the hood. It just happens to be doing it transparently, so you don't ever have to think about it. So, a lot of people are interested in how services are using data keys. So they realize that KMS is in charge of managing master keys, but now the service has the actual plaintext data key that's encrypting my data. How do I know the service is doing the right thing? So we have two different models, and I've named them the EC2/EBS model and the S3 model. I probably ought to come up with better names, but I think for those of you who are familiar with those services, hopefully this makes sense. The idea with the first model is that we have to provision a data key into memory on a host managed by the service so that you can get very high I/O, right? Whether it's EC2 to EBS, maybe you're using an RDS database, which again fundamentally is using EC2 and EBS. Amazon Redshift does the same thing. The idea here is that this data key is going to be provisioned in protected memory in the hypervisor for as long as you want that resource to be active. So your RDS database is active. The minute you say stop or terminate, then that data key goes away. Right? When you want to reactivate the resource because you have submitted a signed API request to do so, that allows the service to say, all right, I'll take the encrypted copy of that data key and pass it back to KMS to get the plain text again. Okay? Now, there are permissions that allow an AWS service to pass that encrypted data key back up to KMS if and when we need to recreate state. So what's a good example of this? Let's say an entire data center loses power, and you had an instance up and running, and attached to that instance was an encrypted EBS volume. It's our fault that power went out. I mean, even if it wasn't our fault, from your perspective, it's our fault. And we want to get your instance back up and running again as fast as possible. Problem is that the data key that is used to encrypt and decrypt data from that attached encrypted volume is gone. It's been wiped from memory the minute the power went out. So how do we get that data key back? Well, we take the encrypted copy of the data key and we send it to KMS under a very defined scope-down permission set that basically says an AWS service can cause this data key to be decrypted if and only if the instance ID and the volume ID match to some previous state, right? Because what you don't want is AWS to have the ability to take arbitrary encrypted data keys, mapping to arbitrary EBS volumes, get them decrypted, and just mount your EBS volume willy-nilly. That would be very bad. So for those of you who have used KMS in depth and looked at AWS CloudTrail events, you'll see evidence where these scope-down permissions, called KMS grants, are created, and they have all sorts of conditions on them to ensure that they can only be used to recreate a known good state. Okay? So services that are built on top of EC2 and use EBS as the fundamental storage layer work this way. The S3 model is a little different because in the S3 case, you are taking this atomic transaction where I've done, say, a put call via S3. Right? When you get the 200 back from S3, you know that that data has been accepted by S3 and they have successfully acquired a unique data key. Or when you make the GET request, S3 has successfully decrypted the data key to be able to decrypt your data. Okay? So the permissions to be able to use your keys in cases where you haven't directly signed an API request, they may exist, but they only exist in the form of roles. Right? So if you think about Kinesis is a good example, right? And we've listed a handful of services down here. Or Athena. You've called an AWS service and you've said, I want you to do some work for me. And that work might take hours, depending on how big your data set is. You are not going to make a signed API request for each and every object that that service needs to get from S3 to be able to decrypt that object. Right? That just doesn't work. So you are effectively allowing the service to create a role in your account that gives it permission to use the KMS master key to decrypt data keys so it can decrypt S3 objects. And in the case of Athena, it pulls in those objects and it does the search that you want it to do. Okay? So when you look at these roles, you'll notice there, again, are all sorts of conditions inside the IAM role created by Athena, Kinesis, SQS. And those conditions restrict the service in terms of how it can use KMS master keys. Because the other thing that may not be entirely intuitive to folks, and let me just go back to this diagram, is that master keys can be used across any number of AWS services. You could use one master key to protect data in all 43 AWS services and n number of custom applications. There's no limit. Now, we do have this model where there are AWS-managed master keys that are designed for customers who don't really care about key management. They just want to check the box. But when you are creating a master key and you own the access policies on that key, it can be used across any amount of data. And in fact, the way we've implemented encryption in KMS is that you could encrypt up to 2 to the 61 number of unique objects under that master key before you start to hit the safety boundaries for AES GCM. Now, I don't know how many times a day you come across 2 to the power of 61, but if you want to create that many resources in AWS, we welcome it. You're probably going to need a bigger line of credit. So we consider that to be practically an unlimited number of objects for most customers. Okay, so those are the two models. And by the way, there's more detail about how services use data keys. We publish that inside the KMS docs. Each service that offers its own encryption will also describe the ways in which it uses KMS. So let's assume for a second that you believe and you understand data key usage inside protected memory of AWS services that are encrypting on your behalf. So a given data key exposes a given data resource. That's the blast radius. So therefore, if you're using a KMS customer master key to protect lots of resources, let's say I have all of my HIPAA data in S3, Redshift, RDS, and I want one master key to protect all of it. Now the security of that master key starts to become pretty important, right? How are those master keys protected in AWS such that they can be made highly available? So I'm going to talk a little bit about the key hierarchy here. If we start down at the data key, you'll see that's a 256-bit symmetric key. That key is encrypted by a customer master key, which is itself another 256-bit master key. And these are generated in what we call hardened security appliances. You can think of the hardened security appliance as an HSM. We decided not to call them HSMs when we launched the service 3 years ago because they have slightly different security properties than most people thought of with an HSM. As a heads up, we will be deprecating the term HSA and be using HSM going forward. When we fully deploy our most recent version of this technology that has been validated in our FIPS 140-2. Regardless, there's a cryptographic module that's generating keys, and that generates your customer master key. Now, that key itself is not stored inside a dedicated host. And that's what's kind of different about KMS compared to classic commercial HSMs, is that master key is encrypted by another set of keys and then stored throughout the service. Why? For high durability and high availability. So what keys is that CMK protected under? Well, each of our cryptographic modules, HSAs, soon to become HSMs, they generate their own set of identity keys using asymmetric key pairs. And those keys never leave the device, and they are only stored in volatile memory. Okay? So your customer master key is encrypted under these keys that are device-specific, and they are stored in lots of places. When they are needed to perform some encryption or decryption operation, they are pulled into an HSA, decrypted in memory, used, and then flushed. So every operation fetches your encrypted CMK, pulls it into these hardened devices, decrypts it, uses it, and then flushes it. Okay? So the relevant thing to look here on this slide is the little titles. I have KMS managed, or AWS service managed. So what I mean here is that the keys inside the HSAs are certainly managed by us. We own the code that generates those keys. The CMK, yes, we generate those keys. We're storing them on your behalf. But you are in charge of their access policies because every key has a key policy associated with it. And you are the only one who can edit that key policy. The data keys, they're managed by you if it's your custom application requesting them via the KMS Generate Data Key API. You're responsible for the plain text and encrypted copies because KMS does not store anything about data keys. You call the Generate Data Key API, we generate 256 bits of random data, we'll wrap it under the CMK that you tell us to, and we return it. And that's the last time we ever see either of those two things. Okay? But if you are using a AWS service, say S3, now it's S3's responsibility to protect that data key. So that's what I'm trying to get across with this slide. So as a summary here, CMKs and the keys inside the cryptographic modules are all stored and managed by KMS, but not data keys. All right, so let's get in even more inside the castle, if you will. What about these HSAs? How are they built? How do you know that those asymmetric keys that we generate that protect your master keys are secured? So we've designed the service in a way that when we make one of these devices operational and it generates its own key pair, it becomes an inaccessible box, meaning no AWS operator can SSH, telnet, connect to it, can't do anything. There is a set of APIs that allow for certain operations to be called on these HSAs, but there is no get key, there is no export key, there is no open up a shell and let me look inside the memory. Those APIs don't exist. The APIs are such that allows keys to be passed in, to be decrypted, your CMKs. It also allows for things like generate random bytes, which we will need to do for generate data key calls. The only way that we can access these hosts is after we put them in a non-operational state. At that point, they've been rebooted. All the key material, if your CMK happened to be in memory at the time, it gets flushed, along with the identity keys of all these devices. Then we can push new code to the device, right? So we think about the threat vector for the KMS service as being the introduction of potentially rogue code, right? If somebody updates one of these boxes and introduces an export API, right? That would be very bad. So how do we prevent that? Well, we have some operational processes that ensure that the person who writes the code has to get 2 independent reviewers. And after those reviewers have approved the code, you need 2 approved operators, not the person who wrote the code, to be able to cause that code to be uploaded to a device. So we're using quorum-based controls to ensure that we are compliant with our SOC control 4.5, which says no single AWS employee can do things that would allow them to gain access to key material. So one of the problems that we have here with the SOC control is that people read that last sentence and say, well, if no single employee can gain access to the key material, then clearly 2 or more can, right? I apologize for this advancing. The answer here is no. The problem is if we introduced code that changed the security properties of the service, then that would take 2 people to introduce that code, which then could potentially allow 1 user. But the way the service is built today and the way we make sure that the SOC auditors validate every 6 months is that the security properties of the service have not changed. In fact, there is no way for anyone to access raw key material. So we are working to see about some ways to change that SOC control. And I would invite all of you who rely on the SOC for evidence of security controls to provide feedback to your account reps or contact us directly through the forums and say, I'd like this SOC control to be changed, or I'd like more detail on this SOC control. We believe that since you're never going to get access to our data centers and we're never going to show you source code, the SOC controls are probably the best way for us to get third-party validation that we're doing the right thing with our services. Okay? All right, let's talk a little bit about how you control access to keys. So the policies on the keys are critical here. So the kinds of permissions that you put on keys, you could, for example, mimic the value of asymmetric key pairs by controlling who can encrypt and who can decrypt. You could do this based on a set of users, a set of roles. You can do this across accounts. You can delineate who has the power to call certain very privileged administrator APIs, like disable or schedule key deletion. When you do cross-account access, you can enable other IAM principals inside external accounts to use the key for encrypt, decrypt, but they cannot do administrative actions. Right? So the account in which the key is created is the only account that can do very significant administrative actions, like disable, schedule key deletion, mapping aliases. Okay? And the policy language for KMS keys is the same as the policy language for all IAM policies. Right? So we evaluate in the same way. All right. The IT security administrator hopefully has a sense of how keys are secured and how access can be controlled. The software developer can use the AWS Encryption SDKs or use service APIs directly and ensure the right keys are being used. What about the compliance team? So CloudTrail gives you evidence of particular KMS requests, like decrypt, which always seems to be the one of interest, when it happened, which key was used. So, of course, every KMS key has a unique 32-character GUID. The encryption context, this gives you a sense of why this master key was used. Remember, the crypto modules in KMS, they don't know anything about AWS services. All they know is they get keys sent in to them from the front end of KMS. And they encrypt and decrypt, and either encryption works or it doesn't work. So we include metadata in requests so that you can see, oh, this master key was used as a part of decrypting this particular volume, or this S3 object, or this Redshift cluster. Okay? Where did the call come from? What was the AWS identity, the IAM principle that made the call? Is this a call that surprises me, or is this a call that I expect? Okay? All right. So let me just touch briefly on some alternatives to KMS, because we recognize that there are still industries, geographies, and IT security administrators that aren't totally sold on how KMS is architected. Maybe the SOC controls aren't doing exactly what you want. You're missing a couple of features. So we provide some options, one of which is Cloud HSM. We also have partner solutions, so you can run your own code or your partner's code inside EC2 and let them handle key management. The Cloud HSM solution, we just recently, back in August, introduced a new version of Cloud HSM. This new version vastly simplifies the ability to provision and operate a dedicated HSM. So the model here is that you get your own slice of hardware that is, in fact, an HSM manufactured by a third party, validated under FIPS 140-2 Level 3. We ensure that the power is on and there's network connectivity, and we will do automatic backups for you and allow you to reprovision these HSMs the same way you reprovision EC2 instances. So you can use a lot of the same tools to manage your HSM fleet. This makes high availability much easier to accomplish. But the important security property here is that you still are the only one who can access the device and cause keys to be created or cause them to be used. There is no AWS data plane API into Cloud HSM. There's no encrypt or decrypt API. You have to use the APIs supported by the third party. And those are all standard-based APIs. For those of you who have done cryptographic development, things like PKCS 11, JCE, CAPI, or CNG. So for those of you who know what you're doing with HSMs, this should look pretty familiar. Okay? So this slide, I know, is a wordy slide, but it evaluates kind of the options for doing key management and encryption. If you start with the KMS service, you are effectively offloading what we consider to be the undifferentiated heavy lifting of secure generation, storage, and access control on keys. Right? Fully integrated with other AWS services, and you can use it directly within your own applications. Cloud HSM gives you a slightly smaller security boundary around the keys themselves. But of course, you don't get integration with other AWS services because there are no AWS managed APIs. Oh, bother. The partner solutions, anything you can run in EC2 works. If you want to roll it all your own in open source, you're welcome to do that as well. All right? And you can mix and match some of these solutions in some cases. Build your own applications and use KMS public APIs. So the model that we're trying to get to is this concept of ubiquitous encryption. We've talked about encryption in transit, using TLS, some of the VPC or VPN services. Your connectivity to AWS services that are doing work on your behalf can be encrypted. You can manage data at rest encryption using fully managed keys inside KMS. You can import those keys from your own on-premise key management infrastructure or use Cloud HSM directly from within your own applications. If you're using KMS, you can restrict access to all of the keys that are being used using policies built inside IAM, and you get a record of every call to KMS inside CloudTrail. And by the way, it's important to know that when I say every call, I mean every call. In fact, calls that we might be making on your behalf. If you file a support ticket and you need to understand, why is my key policy not working the way we want? And we do a get key policy call. That shows up in CloudTrail. Okay? So we're being fully transparent about any and all access to resources inside KMS. Okay. I don't know if this is going to be useful for folks. This might be useful once you get a copy of the slides on Slideware, but I thought I would at least talk about some resources. The KMS Cryptographic Details white paper is pushing about 40 pages. It's something that IT security teams tend to like, especially if they have somebody in there who understands crypto, because it goes pretty deep. The best practices white paper is perhaps more interesting to your ops team. Just trying to figure out, how do I think about blast radius? How many CMKs should I be using? How should I be doing cross-account access? What should I be thinking about in terms of numbers of resources to use and how I want to delegate control of policies? Right? These are all sometimes tough questions if you haven't thought much about key management in the past. Oh, in fact, the best practices white paper, there's a dedicated session on that coming up later this week. And then, of course, compliance reports. So whether it's a SOC report, PCI DSS, KMS is now HIPAA BAA eligible. And as I talked about, the FIPS 140-2 report, it's interesting here, that information is public because NIST has publicized it on their website. But we are in the process of migrating all of the KMS infrastructure to that approved cryptographic module. Because we have to do that across 15, 16 plus regions, it just takes time. So you'll see a formal announcement from us probably right after the new year. Okay? Other sessions that you might want to look at, I talked about the best practices, a deeper dive on the new AWS Cloud HSM offering, and then we have a workshop about using the AWS Encryption SDK. So developers in the crowd, I highly recommend you attending that one to learn more about how we're trying to simplify client-side encryption. Okay, we have a couple of minutes left. I understand that people can come up and ask questions if you want. You can do it publicly in the microphone, or I will be here for 10 minutes or so after the presentation ends, and you could always grab me out in the hall until the next session starts at 12:15. Okay, thanks a lot.